Okay, so you're welcome to lecture 4 notes, okay, or lecture 4. We are just, in the previous lecture, we ended on conditional probability, and we now move on to decision trees or tree diagram. Now, we have seen a contiguous table before in the previous lectures. Okay, so a decision table, a decision tree is an alternative to the contingent table. Okay, so let's have, from the previous lectures, we're given a table. So let's have that. Okay, so in this table, this table just represents the purchase behavior. Okay, so we have a table that represents the purchase behavior for 1,000 households, okay, in terms of purchasing Tesco units. Now, the table is given as follows. Yes. So we have okay. Okay, so we have those that planned to purchase, and those that actually purchased. Okay. So here we have those that planned and those that did not plan. Then we have those that actually purchased and those that did not purchase. And we have the total there. Okay, so 200 there. We have 100, 50, we have 650, we have 250, and 750. So the total there, just 1,000. Okay, then we have that 700 there. Okay, all right. So I think I'll just omit the totals. All right, so we see that those that planned to purchase, in total, we have 250, and those that did not plan to purchase, we have 750. And for the people that actually purchased, we have 300 there, 700, and our total is 1,000. So we calculated some probabilities based on this table, but now we're going to show how we can construct a tree diagram or a decision tree on this. Okay. Okay, yeah, so I'm going to continue. All right, so we're going to construct our decision tree as follows. We'll have just 2 branches there, And these are the ones that planned to purchase. And these did not plan to purchase. Okay, then there we again have two branches. We have those that actually purchased, okay, and those that did not plan. Okay, I'm shortening it as that. Then there we have two branches. Okay, so we have the two branches. Again, we have those that actually purchased. And those that did not. Okay, so actually here, we have those did not actually purchase. Did not actually purchase. Okay, did not. In here, we have did not actually purchase. Okay, so that is how our tree diagram will look like. Okay, and we can actually calculate different probabilities based on this tree diagram. Okay, so here we can get the probability of those that planned to purchase. Okay, so these ones planned and actually purchased. Okay, there we have those that planned to purchase and did not actually purchase. Okay, from that branch we have those that get the probability of those that did not plan and actually purchased. Then finally, we have the probability of those that did not plan and they didn't also actually purchase. Okay, so those are the probabilities that we can obtain from our tree diagram. All right, let's have the second example. Okay, so in example 2, we're given that the Zambian team soccer team wins, which is W, with probability 0.6, loses L with probability 0.3 and ties T with probability 0.1. The team plays 2 games over the weekend. Okay? So what is the probability that one, the team wins at least once? Second question is, what is the probability that the team wins? So the team wins at least once, and does not lose. Okay, and the last question that we should find is the probability that the team loses and ties. Okay, so we should find those probabilities. So we need to create a decision diagram. Okay. So we are going to have our tree diagram. We are going to have 3 branches which represent a win, a loss, and a tie. But remember, the team played twice. So these branches are going to have further branches. Okay, so for each branch we'll have 3. Which is the win, a loss, and the tie. A win, loss, and the tie. Win, loss, and the tie. Okay, so what are the probabilities that we get there? We have a win, win. We have a win, loss, win, tie, lose, win, lose, lose. Okay, so those 2 losses, a loss and a tie and the win, tie and the loss, tie, tie. Now, the first question, we're asked to find the probability. Okay. So in the first question, we need to find the probability that the team wins at least once. Okay, so what are these probabilities? The team wins at least once. At least means that it can be 1 or more. So wherever we find a win, so we'll get that, that. Okay. Okay, so this gives us the probability of win-win plus the probability of win-lose plus probability of win-tie plus probability of lose-win, and finally the probability of tie-win. Okay, so there's something that we have not added on our tree diagram, and those are the probabilities. So for win, we have a 0.6. For a loss, we have 0.3. And tie, we have 0.1. So there the win, again 0.6, 0.3, 0.1, 0.6, 0.3, 0.1, 0.6, 0.3, 0.1. Okay, so to get the probabilities, remember these are mutually exclusive events, so you just multiply the probabilities on each branch. Okay, so therefore, probability of win-win is just 0.6 multiplied by 0.6 plus win-lose is 0.6 multiplied by 0.3, then plus win-tie, which is 0.6 multiplied by 0.1 plus lose-win 0.3 multiplied by 0.6 and sky win 0.1 multiplied by 0.6. Okay, so you add those probabilities and you get 0.84. Okay, then we go to the next question. So this was our one. The next question, our two, we need to find the probability that the team wins at least once and does not lose. Okay, so we go back to our tree diagram. We first want a win. Okay, so it should win at least once, but it should not lose. So this goes. The other one has a win and a lose, but we don't want a loss. So we'll skip that and we'll put that. So we have win-win, win-tie, and tie-win. So this is the probability of win-win plus win-tie plus the probability of tie-win, which gives 0.6 times 0.6 plus 0.6 times 0.1 plus 0.1 times 0.6. And this will give you 0.08. Okay, so we go to the final question. We need to find the probability that the team loses and ties. So we go back to our tree diagram again. Wins, losers and ties. That's that and that. Okay. So we just have tie win and tie lose and lose tie. Okay, so this is just the probability of that and that, which is just 0.3 times 0.1 plus 0.1 times 0.3. And this gives us 0.06. Okay, so that's where we're going to end with decision trees. Yeah. So we move to our next subtopic, which is posterior probability. So actually, posterior probability, so the posterior probability of an event is just simply so let me just say the posterior probability of an event is the conditional probability. So the conditional probability that is assigned, okay, after relevant evidence. Okay, so this is an extension of conditional probability. And to find this type of probability, we use the Bayes theorem. Okay, so this is a very interesting theorem. It was discovered by a reverend by the name of Reverend Thomas Bayes. Okay, so in his investigation, he came up with a theorem. Okay, so let's explore this theorem. Okay, so recall using conditional probability that the probability of A given B is just simply the probability of A intersection B over probability of what? B. Okay, now we can do cross multiplication here. If we want to find the probability of who? A intersection B. So this is just the same as probability of B multiplied by the probability of A given B. Okay. Now, note this again. We can use therefore this probability to find the probability of B given A. Okay, so the probability of B given A, we know this is the probability of A intersection B over what? probability of A. Now, suppose we don't know A intersection B, but we know the probability of A given B and the probability of B. We can use this, okay? So, because this is just the same as the intersection. So, you can say that A intersection B is just the same as the probability of B multiplied by the probability of A given B over the probability of what? A. Okay, so we have used the probability that we know, the conditional probability that we know, to find the conditional probability that we do not know. Okay, so that is our starting point. Okay, so we move on. Okay, so Bayes' theorem is actually an extension of what we have just seen. So let's have let's look at an example. So, in this example, we have 3 machines. Okay. So, suppose 3 machines, A, B, and C, produce similar engine components. Machine A produces 45% of the components, then machine B produces 30%, and machine C produces 25%. Now, we are told that for the usual production schedule, 6% of the components produced by B, 6% of the components produced by machine A do not meet the established specifications. In short, they are defective. 6% of machine A are defective. Okay? And we're told that of machine B, 4% are defective. And from machine C, 3%. Of machine C are defective. Now, we are told that one component is selected at random from the total output and is found to be defective. What is the probability that the component selected was produced by machine A? So that is our question. Now, what we notice here, we can put it in a diagram. Okay, so we have machine A producing the component, which is what? Machine A produces 45%. Okay, and we have machine B producing 30%. So this is 30% of the engine products coming from B. And from C, we have the 25%. Okay, but of the components produced from machine A, we have some defective. So actually, all of them produce defective. So here we have 6%, B has 4%, and C has 3%. So these three machines all produce defective. Now we're told that one component is selected at random from the total output and is found to be defective. What is the probability that it came from machine A? Okay, so that is the probability that we are looking for. So in short, we are looking for the probability that a component is coming from machine A given that it's defective. Okay, it's coming from machine A given that it's defective. So from conditional probability, this is just the probability of A intersection D over what? Probability that it's defective. Okay, now the probability that a component is defective will come from the following. Okay, so maybe let me just do this. Let me just take out these numbers so that it creates some space. So the probability that we have a defective is just that, the probability that it's coming from machine A and defective, a component is coming from machine A and defective, plus a component coming from machine B and defective, plus a component coming from D and defective, or C. C and defective. Okay, so this is how we find the probability that a component is defective, because the defectiveness comes from all the three machines. Okay, but how can we find, okay, maybe let's look at the probabilities that have been given. The probability of A, we're given as 45%, which is just 0.45. Okay. Then we're given the probability that a component is defective given that it's coming from A, which is 0.6%, which is just 0.6. Maybe let me create some space for that. Okay, so maybe let's have just that. Okay, then let's just put the probability of B is 30%, which is just 0.3, and the probability of C is 25%, which is 0.25. Okay, then we are also given the probability that a component is defective given that it's coming from machine A is 6%, which is 0.06. And we've also been given the probability that it's defective given that it's coming from machine B 0.04, which is 4%. The probability that it's defective given that it's coming from C is 0.03, which is 3%. And remember, if we have the probability of D given A, this is just the probability of A intersection D over what? Probability of A. So you can cross multiply to get the probability of A intersection D, which just gives you the probability of A multiplied by the probability of D given A. Okay, so here when we're looking for the probability of D, we need to use this, the probability of A intersection D. But we don't have the probability of A intersection D. So, therefore, we just use this statement here. This one. Okay. And D replace with the probability of A intersection D. Therefore, the probability of D, okay, so now we now come back to the probability of D. Where there's A intersection D, we just put the probability of A multiplied by the probability of D given A. And similarly, the probability of B intersection D will have the probability of B multiplied by the probability of D given B. And the probability of C intersection D will have C multiplied by the probability of D given C. So remember, this is our question. Okay, this is our question. In answering this question, we have just found that the probability of D is given by this statement here. Okay. And the probability of A intersection D, remember A intersection D is just this. Okay, so therefore we have all the terms that we are looking for. So let's rewrite. So therefore, the probability of A given D is the probability of A intersection D over the probability of D. But what is the probability of A intersection D? We are not given. So we replace with the probability of A multiplied by the probability of D given A. And the probability of D as well, we are not given. But we know that this is the probability of the probability of D intersection A plus the probability of, I'm just rewriting what we have already discussed. B plus the probability of D intersection C. Okay, but we know D intersection A we're not given, so we use the conditional probability. So this is just probability of A multiplied by D given A over the probability of A is always the same as the numerator, A multiplied by D given A plus probability of B multiplied by the probability of D given B plus probability of C multiplied by the probability of D given C. So this is our formula. And actually, this just represents the Bayes theorem. Okay. So this represents the Bayes theorem, we have all these terms, so we can just put them. Okay, so this will give us the probability of A given D, the probability of A is 0.45 multiplied by, so sometimes I put the cross and sometimes I just leave it like that without any sign. It just means multiplication. Okay. Now down there we had the probability of A multiplied by the probability of D given A plus the probability of B multiplied by the probability of D given B plus the probability of C multiplied by the probability of D given C. So this gives us 0.027 over 0.027 plus 0.012, 0.0075, 0.027 over 0.0465, which gives us 0.581. And that is the probability that we have been looking for. Okay, so in short, the Bayes theorem just states that okay, so in short, the Bayes theorem just states that the probability of AI given E is just the probability. Okay, so this is 1. A1 given E, just the same as the probability of A1 multiplied by the probability of E given A1 over, you get all the partitions. A1 multiplied by the probability of E given A1 plus the probability of A2 multiplied by the probability of E given A2. So you go on plus until you have the last partition, probability of AN multiplied by probability of E given AN. So that is the Bayes theorem. Okay, so we're going to move to more examples. We're going to move to more examples. Okay, so let's look at okay, so we're going to look at that example. Okay, so we're going to look at that example. This was an assignment question. This was an assignment question last semester. Okay, so in this question, we're given that a new medical drug to cure HIV/AIDS has been developed. The probability that it will cure HIV/AIDS is 0.9 if the patient has HIV/AIDS. The probability that it will cure HIV/AIDS falls to 0.4 if the patient does not have HIV/AIDS. There is a probability of 0.3 that a person chosen at random from the community has HIV/AIDS. Find the following. The first one is probability that a patient is cured of HIV/AIDS, and the second one is to find the probability that a person cured of HIV/AIDS actually had HIV/AIDS. Okay, so that is our question. So we are going to have our solution. Okay, so that was example 3. Actually, it's example 2. Okay, so in this example, let's see be the event that a person is cured. Okay? And the event has HIV/AIDS be represented by H, not cure. Okay, so this will be cured. Not cured will be represented by C bar. Put a bar on top there. And doesn't have HIV/AIDS will be represented by H bar. Okay. Therefore, we are looking for first the probability that a person is cured. So the probability that a person is cured will be the probability that the person is cured and had HIV plus the probability that a person is cured and didn't have HIV. Okay. But the person is cured intersection H is just the same as the probability of H multiplied by the probability of C given H plus the probability of H not having AIDS by C given not having. Okay, so those are the probabilities. And then we continue. Probability Okay, so maybe let me just put that again. H bar multiplied by the probability of C given H bar. Okay, the probability of having HIV/AIDS is 0.3. The probability of being Q1 when you have HIV is 0.9. Then we're going to add the probability of not having HIV/AIDS. Now this was not given, but since we are given the probability of having HIV/AIDS, which is 0.3, therefore we know that all probabilities should add up to 1. Therefore we're going to say 1 minus 0.3 is 0.7, which gives us the probability of not having HIV/AIDS. So this is 0.7. The probability of being Q1 when you don't have HIV/AIDS is 0.4. Then compute those, and we're going to find 0.51. The second question we are told to find the probability of being HIV given that you are cured. Okay, so this is just the probability of H intersection C over the probability of C. But we already have the probability of C. So up there we have this multiplied by the probability of C given H over probability of C. This gives us 0.3 times 0.9 over what? The answer that we just found. And it will give us 0.49. Okay, so we are going to, we have seen how we can find the probabilities using the conditional probabilities that you've been given. Okay, so we are going to end here. In the next section of this unit, we're going to talk about counting. We're going to talk about counting techniques together with an introduction to probability distributions. Okay, thank you.